So first, thanks to Derek and Bill for inviting me to talk here, based on knowing almost nothing about me, which is very brave of them. I've got to confess that this talk isn't really about Haskell. It's sort of incidentally about Haskell. So all of the code is going to be in Haskell, and that's mainly because I know Haskell and most of you guys know Haskell, but really the same talk could be done with all the code in ML, or it could be done in Scala instead, any language that has algebraic data types, because really this is just a talk about types. So on the scale from super theoretical to super practical, it's kind of more towards the theoretical end. But hopefully it'll be pretty interesting. So I started learning Haskell about a year ago, pretty much dead on a year ago, when I was working for an investment bank, writing Java all the time, and had just come out of studying maths for 8 years and wanted something that was going to exercise the maths part of my brain rather than the writing Java part of my brain a bit. So picked up Learn Your Haskell and picked up Real World Haskell and read those and thought, hey, this language is pretty awesome. And then started going on Stack Overflow and reading blogs and that kind of thing. And all the time I was doing this, I kept noticing that people would use mathematical-like terms when they were talking about Haskell. So people would talk about product types and sum types and that kind of thing. And it got me wondering whether there was actually anything behind this. Like, is there some theory? Is there some connection to maths? Or are they just names which are just there by coincidence? So I started playing around with some types and blog posts about it. And after having thought I discovered some really interesting things, went on to Stack Overflow and posted this question about it. So this was in February this year. This question has about the first 6 slides of the talk in it, so if you read really fast, you can just go to sleep for the first 6 slides. And got some fantastic answers on this question. And the talk is going to be about me explaining those answers and seeing how far I can push the connection. Haskell guru, who's written a lot of libraries. He wrote the Xmonad window manager, if anyone uses that. And he explained algebraic data types by saying that Haskell's algebraic data types are named such since they correspond to an initial algebra in category theory, giving some laws, operators, symbols to manipulate. And I immediately went, category theory, initial algebras, what the hell? This scared the hell out of me, and I decided not to think about this for about another 2 months. And it wasn't until much later that I realized what I'd done is focus on the wrong things about what Dom was saying here. So what I should be focusing on is algebras are just things with symbols, operations, and laws. And actually, it's really great that you have a whole bunch of category theory backing it up. And it's great that Haskell's types form an initial algebra in a category. But to actually get some intuition and understanding of it, you don't need to know about any of that. So this sentence is going to be the last time that I say the word category in this talk, and everything else will be much lower level. Okay, so algebra is something that most of us learned at school, and we have a bit of an idea about what it is. I'd like to present a couple of different algebras, and then give some sort of higher overview of what algebra is. So according to Don Stewart, an algebra is something that has symbols, operations, and laws. So here's an example of algebra. This is the algebra you learned at school, where the symbols are numbers. So you have 0, 1, 2, they go on. You might have a half, you might have pi, and then you can have x, y, and z, which can stand for any other number or maybe something else. And then the operations that you learn about in school algebra are addition, subtraction, multiplication, division. There can be more of these, so the factorial is an operation. So these are things that aren't numbers themselves, but you can take numbers and give it to one of these operations and they give you back another number. Okay, so plus is a binary operation, you give it 2 numbers and it gives you back another number. And then there are laws in school algebra as well. So one of the laws is that 0 plus x is x. Okay, if you add 0 to something, you get the same thing back. So that's an example of an algebra. Haskell types are an algebra as well. So here the symbols are types themselves. So this guy up here is what people call unit. Okay, it's the most boring type. It only has one value, which is unit, and it's what you use if you return something from a function. You don't care what you return, but you have to return something, so you just return unit instead. And then you have ints and bools and lots of other examples. All of these, incidentally, are examples of finite types. Int is sort of conceptually supposed to be infinite, but really there's only 4 billion or so of them. And you have infinite types as well. So integer, for example, is an example of an infinite type. There are infinitely many different values that an integer can have. And then the operations are type constructors. So these are things that aren't types themselves, but if you give them a type, they give you a type back. So maybe is an example. Okay, there's no such type as maybe, but if you give maybe another type, like int, you get maybe int, which is a type. So these things, not types themselves, but they're the operations in this algebra. And laws, we don't really know what the laws of the Haskell algebra are yet. Maybe you already do, but I haven't said anything about it. So we'll see some of those in a while. The key point I want to make here is that we're concerned with Haskell's types, and we're going to be doing computations with the types. We don't really care that much about the values, which is sort of the opposite to when you're actually programming, when you care a lot about the values. So here's the overall high-level view of algebra, which is that symbols are just things. Operations are ways to make new things out of the old things. So you take one or two or more old things, and you put them together and you get a new thing. And laws are rules that things follow. And I'll explain this a bit more as we go on. Okay, I have a short prelude. I had this idea that I wanted to make the talk executable. So there will be some code in the talk. And if you are sitting with a laptop, either now or later, you'll be able to type in that code. And if you had a text editor, had GHC, you could then compile it, and you see that it compiles. And when it compiles, you know that I've said something which, at least if not right, is type safe. So if anyone does have a laptop, you can type in the code, and if it compiles, that's great. If it doesn't, then either you've made a mistake or I've made a mistake. So check that you've made a mistake. And then if you definitely haven't, then tell me that I've made a mistake, and everyone will benefit. But if you want to do it, you need to have this language pragma at the top, otherwise it won't compile. Okay, so the simplest, one of the simplest objects in maths is the number 1. And I'd like to work out what the Haskell version of 1 is. And when people are writing papers about this, they call it unit rather than calling it 1. Okay, but it's just a name. And the key thing to realize about unit is that it's a data type called unit, and it has one constructor, which is also called unit, and the constructor doesn't have any arguments. So there's only one value of type unit, and it's just unit. So it's kind of boring, but it's important to have it. And now that we've defined 1, I could go on and define 2 and 3 as well, and I could keep going, and it would get fairly tedious. Actually, what would be even better is that now we've got 1, if we had a way of saying 2 is just 1 plus 1, and 3 is 1 plus 1 plus 1. So to do that, we need to define what addition is. This, by the way, is the way that you typically see unit written in actual Haskell code. There's just a pair of open and closed parentheses. So to define addition, this is why we need this type operators language pragma, because I want to do things like this. So if I break this down, all it's saying is that you've got a data type, which has 2 type variables, a and b, as its arguments, and we call it a plus b. And to say that you have an a plus a b, well, people call this either a disjoint union or a variant type or a sum type. It means that you've either got an a or you've got a b. So here you can see that you either have an a or a b, and if it's an a, you've tagged it with an add-l type, and if it's a b, you've tagged it with an add-r type. And this is mainly useful if you know that your function is going to want to either accept or return one of 2 different things, but you're not sure which one at compile time, so you let it do both. And the people who wrote Haskell were smart and realized that people would actually want to do this quite a lot, and so they called this thing either. So these 2 things are exactly the same as each other, they just have different names.
You can explain why having either A or
Yes. So let's give an example here where we'll make it concrete and say A and B are both Boolean. Now, remember I said the important thing about unit, or 1, was that it only had one value. Boolean has two values, because it has two constructors, false and true. And now we can say, right, how many values does bool plus bool have? You're either in the left case or you're in the right case. If you're in the left case, then you could be left false or left true. And if you're in the right case, you could be right false or right true. So there are 4 different values. Given that a Boolean has 2 values, then Boolean plus Boolean has 2 plus 2 values, which is 4 values, which is why we refer to this as an addition. Thank you, Peter. Okay, multiplication. Here, the type version of multiplication is that instead of having either an A or a B, you have both an A and a B. Another data type, A times B. And here we have a single constructor, and it has 2 arguments, so it has to have both an A and a B present. And so if we wanted to give the same example we gave for addition with 2 bools, then the first argument could either be true or false, and the second argument could either be true or false. And there are 2 times 2 different values. Again, there are 4 different values for bool times bool. Just to give something different to the previous case. So if it was some type which had 3 different values, say A, B, and C, then there would be 9 different possibilities for this type. And again, the people who designed Haskell were smart and realized people would want to use this a lot, so they called it pair. So pairs corresponds to multiplication. Zero is a tricky one. We definitely have 0 in school algebra. You don't really have it in Haskell. So I went to the paper, A History of Haskell Being Lazy with Class, which is by these 4 guys at the bottom. And they say that in general, an algebraic type specifies a sum of 1 or more alternatives, and each alternative is a product of 0 or more fields. It might have been useful to permit a sum of 0 alternatives, which would be a completely empty type, but at the time, the value of such a type was not appreciated. I think this is a bad Haskell pun. What we're going to do is do what the designers of Haskell would do if they could go back in time and do it properly. So this is why we need the empty data declarations language pragma at the top. So 0 is generally called void in the computer science literature, and you just write a data type called void, and it doesn't have any constructors at all. So it's impossible to actually make a value that has type void, which makes sense, right? Void is supposed to be 0, and it has 0 values, because you can't construct one. This is the most zen slide of the talk. The rest of them will have more content on them. Yes, so undefined is a really good point to make. I'm not going to mention it for the talk because a lot of what I'm going to say, if you have undefined values, doesn't really work. Because undefined, or bottom, is a value that matches every type. Okay, so if you write x equals undefined, that happily compiles because undefined can be any type. A lot of the things I'm going to say don't really work when you have undefined, so I'm going to happily ignore it for the rest of the talk. Okay, and while we're here, we might as well define 2. So I said that 2 is just 1 plus 1, so 1 was called unit. And here we can just make this a type. Okay, so we don't have to say it's a data declaration, it's just an alias. 2 is 1 plus 1. And again, a very useful thing to have. And so the design of Haskell gave us bool. So I'll alternatively refer to either bool or 2 throughout the talk, and they mean the same thing. Okay, it's something that has 2 possible values. Okay, so here's a bit of a recap and some notation that we use. So the void type is our 0. Void doesn't have any values, has 0 values, and we write 0 for it. The unit is what we're calling 1. It only has 1 constructor, and it has 1 value, and so we write 1 for it. Bool, we'll occasionally write 2 to mean bool, or we could mean anything that has two constructors. Addition takes two type variables, a and b, and we'll write that as a plus b. And multiplication takes, again, two type variables, and we'll write that as a dot b. And the reason I'm using a dot instead of a multiplication sign is because there's going to be x's around, and I don't want to get confused with multiplication and x's. So here are some laws of the Haskell algebra. And what's nice is they actually correspond to a lot of the laws from school algebra. So 0 plus x is equal to x is a good law from school algebra. And if we give it a type interpretation, then we will be saying that either void or x is the same thing as x. And this symbol here, this curly equals sign, I'm using because if you use the Haskell double equals sign, these things would not be equal. They don't have structural equality. They have a kind of semantic equality, right? They mean the same thing. What I mean is you could write a function which, given an either void x, gives you an x, and you could write a function that, given an x, gives you an either void x, and that correspondence is 1 to 1. Okay, so they're essentially the same thing. So we can check that this is true. So either void or x means you either have left void or right x. And how many values of left void are there? Well, there aren't any, because you can't get a void to begin with, so you can't have a left void either. So you can't even have the left constructor. You can only have the right one, which is why it's just the same as having x. Another law is that 0 multiplied by anything is equal to 0. Okay, it's definitely true for numbers. And that would be the same as saying that the pair of void and x is the same thing as void. Well, this makes sense, because you can't ever get a value to put in the first slot of this pair. So that means you can't have the whole pair. So I'm fairly happy with this guy. Another is that 1 times x is equal to x, which, given a type interpretation, is saying that the pair of unit and x is the same as having an x. This makes sense because you know there's only one possible value that can go in the first slot of this pair, and that value is unit. So given that you always know what's going to be there, there's no point having it at all. Yeah. Sorry, the... Yes, it won't type check. So they don't have, the types are different, but they are equivalent to each other. So they're isomorphic to each other. If you had one, you could always write a function which gave you the other one. So you could write a little helper function which converted to the right type whenever you needed it. Exactly, yeah. Yep. Yep. You can, yes. So if you had the function second, which would just take the second part of the pair, and you gave it a void x, then it would happily give you the second part of the pair. Exactly. There's no way you can get a void x from to pass in. Yes, I'm happy for you to say that. Is that okay? Okay, so if we are done with this slide, another law is that x plus y is the same thing as y plus x. So having an either xy and an either yx is a relatively simple function to take one of them and give you the other, which is that you just exchange all the lefts and rights. So these two things have this semantic equality. And the last law I'm going to look at here is that x times y is the same thing as y times x. And all you'd have to do here to convert an xy into a yx is just swap over the two elements of the pair. So these laws which hold for numbers also hold for Haskell types, as long as you are talking about this semantic equality rather than the Haskell double equals default, which compares for structural equality. We haven't talked about functions yet. And functions are kind of important to Haskell. One of its defining properties is that functions also are types, right? So you can have function types. And I think the best way to figure out what the algebraic equivalent of functions is to do a couple of examples first. So any function has a domain, which are the set of all the inputs, and a range, which is all of the possible outputs you could have. So the function that takes a bool to a bool has its domain as true and false, and its range also as true and false. And now, so far we've had this kind of counting correspondence in that the name of a type has been the same as the number of values of that type. So bool we called 2 has 2 values, unit we called 1 has 1 value. So we could try counting the number of functions there are here and see if we can use that to give us some kind of algebraic correspondence. So a function is just a mapping from the domain to the range. And the number of functions here, well, either both true and false could map onto true. So these arrows down here, so that's 1. Or both true and false could map onto false down here, so that's 2. Or you could have the identity function, where true maps to true and false maps to false. Or you could have the function which swaps true and false. So there are 4 different functions from bool to bool. And a way that we could have done that without enumerating them all is to realize that true can map to 2 different values, and false can map to 2 different values, and 2 times 2 is 4. 2 times 2 is also 2 squared, which will become important in a second. If we had 3 different values in our domain instead, a, b, and c, we can ask how many functions there are here. I'm not going to list all of them, but we can do the same kind of counting argument. So a can take 2 values, b can take 2 values, and c can take 2 values, and 2 times 2 times 2 is 8. It's also 2 cubed. And if we had 3 different values on the bottom, then we'd have 3 times 3 times 3, which is 3 cubed, which is 27. So 27 different values from a domain of size 3 to a range of size 3. And the argument works certainly for any finite type, in that if you have a different values in your range, a different values in your domain, and b different values in your range, then there are b to the a functions between them. So this motivates writing functions in our algebraic world as b to the power a. So this definitely works for finite types, and for infinite types, we're just going to keep the notation, even though it might not make any sense to say what's b to the power of infinity. We're just going to work with it and see where it leads us. So let's look at a couple of function laws. So a law of high school algebra is that 1 to the power of anything just gives you 1 back. So in the language of types, this is saying 1 to the a is functions from a to unit. So a to unit is the same as unit. Does this make sense? Well, it makes sense because there's only one function from a to unit, which is that every single value maps to unit. Okay, it's just the function is const unit. So given there's only one function, you might as well just say it's unit. Okay, so these two things are semantically the same. A to the power 1, so that's the same as a if you're working with numbers. And in typeland, that represents the function from unit to a. Now any function which takes a unit and gives an a, well, you decide what the entire function is just by picking what its output is going to be. Okay, so it's only got one possible input, so there's only one possible output value it could have. And so its output, the choice of output determines the entire function. So there are the same number of functions as there are potential outputs. So we can say that the set of functions from unit to a is equivalent to a itself. This is a trickier one. So this is saying the exponent rule from algebra, so that b times c to the power a is the same thing as b to the a times c to the a. Again, works for numbers. In types, it has this interpretation that if you have a pair of functions, an a to the b and an a to the c, you can factor out the inputs to them. So you could write that function as something which takes an a and returns a pair, b and c. This is something that's actually you sometimes see used in real-world Haskell code. So the The data lens library, for example, uses exactly this transformation. So without getting into it too much, in the lens library, you have two functions which are a getter and a setter, and they have a common input, which is the object whose properties you are getting or setting, and so in the code base they're just factored out into this form, which gives you some minor efficiency gains. And here's the final function law I'm going to look at. So c to the power of b times a is the same thing as c to the b to the power a. And if we translate that into type land, well, on the left-hand side, you've got something from a pair a and b to a c. And on the right-hand side, you've got a function which takes an a and gives you another function from b to c. And this is exactly currying and uncurrying. Okay, so this is the curried version of the function, where it consumes the parameters one at a time. This is the uncurried version of the function, where you have to pass in a pair of both of the inputs. All of these algebraic laws have type-level equivalence. Is that a question at the back? Okay. So we haven't talked about recursive types yet. And the example I'm going to start with, because I think it's the most familiar one, is lists. So if you read real-world Haskell, and you'll get onto about chapter 4 or so, and it'll explain how linked lists work in Haskell, that a list is either nil, which is the empty list, or it's a const of x onto another list. Okay, so a list is either empty, or it's a head with a tail. And we could translate that into our algebra and say that a list of x's is either a unit, which is empty, okay, it's just something with one constructor with no values, or this plus, it's a value at the head of the list, and then another list afterwards. That's the product here, saying we have to have both of those things. That's actually, there's a lot of line noise there, so I'm going to write it a little bit more succinctly, and just say that a list is 1 plus x times another list. And this is where I was going when I started playing around with these kind of equations, and I wondered if you could solve this equation to find out what L is. So you can remember some school algebra, and because it's a recursive type, just substitute in. So we know that L is 1 plus XL, so we substitute that in, and then we have another equation where we haven't really got very far because we've still got an L here, but it's recursive, so we could just substitute in again. And we keep expanding out this and doing this, and we carry on doing it, and eventually we get a term that looks like this. So this is just repeatedly substituting the value of L on the right-hand side with the entire expression on the right-hand side. And what this is saying is that a list is either empty, or it has one value, or it has two values, or it has 3 or 4. So it's a list, right? So this is kind of neat. Have this big long infinite sum and say this algebraic expression corresponds to the type of lists. But there's a neater way we can do this if we're happy to completely abuse the algebra. So we start with our initial equation. A list is 1 plus an x and another list. And say, well, what happens if we try and get all of the L's on one side of the equation and solve? So we take this xl to the other side of the equation, and we factor it out. So we get L times 1 minus x is 1, which now makes no sense on a type level at all. Right? This is utter nonsense. What the hell does 1 minus x mean? But we just work with it and say that this means that lists are 1 divided by 1 minus x. Now, if you ever studied an A-level in maths, you'll remember there's a thing called Taylor's theorem, which essentially tells you a way to start with a function like this and express it as a sum of different powers of x's. And you can go to Wolfram Alpha, and you can type in this, and it will tell you that the function you're after is 1 plus x squared, which is exactly what we had before. So we can totally abuse the type algebra, do completely unjustified things, and you get neat results out of it. A slightly more complicated example is trees. So a binary tree. So we're going to have a binary tree which has empty leaves and its values at the nodes. So that's either an empty tree, which we call the tip of a tree, or it's a node, which has a value x and a left tree and a right tree. So translating this into algebra, we can write that t is 1, which is the empty tree, or it's a value x and two other trees. So I could write t times t here, but I'm just writing t squared. And then we can try and apply a little trick again, right? So we just pretend that these things aren't types, they're just numbers, we do whatever the hell we like with them, and we see what happens. So we collect everything onto one side of the equation, and this isn't quite so straightforward anymore, but you might recognize this as a quadratic equation. So if we have a brief interlude to talk about quadratic equations, you'll remember that you can solve them with the quadratic formula. Okay, this is something which I was totally surprised to find a use in types for, but this is the quadratic formula. So if you've got an equation, ax squared plus bx is c, you get this horrible looking thing which tells you what the value of x is. And there are two possible values of x. Right? So quadratic formulas have two different solutions. I'm going to ignore that for the moment. So we'll go back to where we were. So we've got this equation for trees, and we'd like to solve it using the quadratic formula. So we do that, and we get utter nonsense out. Right? This makes even less sense than the list example did. Okay, so we've got another one of these subtractions of types, and then we take the square root of the type. And we subtract that from something else, and then we divide by a type as well, just to really screw with our brains. Okay, this is nuts. But you can just go to Wolfram Alpha and say, hey, Wolfram Alpha, what is the power series for this? And it will happily tell you that this is the same thing as this power series. This doesn't have quite such a nice interpretation. So it seems to be saying that trees could be unit, which is just an empty tree, that's fine. Or they could have one value, so that would be a node and two empty trees. And then there's a bunch of other stuff. So I went through and tried to see if this made any sense. And in fact, it turns out it does. So here's the equation at the top. So first it's saying a tree could be empty. Okay, this is my empty tree up here. It's light blue because it doesn't have any values. Or you could have an x, which is a tree with one value. So a binary tree with only one value is just a dot. Okay, both its branches are empty. Or it's saying there could be two different kinds of trees that have two values. And if you go and draw the trees with two values, you find there are these two. Okay, you have a node, and it either has a left value or a right value, and everything else is empty. And I went and did the trees with three values as well, just to show you there are 5 of them. And then I couldn't be bothered to draw the diagrams anymore, so I didn't do 14. But it's actually quite fun to go and work it out. Fun. If you spend 8 years studying maths, you think this kind of thing is fun. So this is actually neat. It's telling us that trees can have 1 or 2 or 3 or 4 or 5 values, and also the coefficient in front of it tells you how many different trees of that kind there are. And so if we think that, say, x could be Boolean, right, x is just a type variable, it could be any type, so if it's Boolean, so if we start substituting that in, that would say, let's take this x term, for example. There are 2 Boolean binary trees with one value. Okay, that value is either true or false. If we substitute it in here, so we say x is 2, then there will be 8 binary trees that have Booleans as their values. And you can go through and label them all. Right? It's basically looking at these and saying which ones can be true and which ones can be false, and count them up. So I thought that was pretty neat. And that was essentially as far as I managed to get on my own, and the point at which I needed to have help from people who know a hell of a lot more about this stuff than me. Yeah.
One question I wanted to ask before square root. Now I can see a square root in there, and I still don't know. But it looks like that's taking that square root of it.
Well, yeah, certainly. I agree this is nuts, which is why I thought it was so cool that you can do this stuff, which is clearly completely unjustified, and get nice results out of it. Now, what's kind of fun is there's a paper by a guy called Tom, who's a mathematician who last I checked works up in Glasgow, who's written a paper showing that you can take the algebra of types, and he describes it properly mathematically and says this is a semi-ring, which is a mathematical object, fine, and says that you can do all these unjustified operations on there as long as they're fine for complex numbers. So if x was a complex number, completely legit, right? You can definitely take square roots of complex numbers. And as long as a couple of conditions are satisfied and you get a sensible result at the end, then it's still true for types. So he does basically all the background which you'd need to show to to say that this stuff is actually justified, which I'm totally skipping over because I don't understand it. I hold my hands up. Yes, but I'll get to them toward the end of the talk. Certainly divide, minus is trickier. Okay, short diversion here to talk about zippers. So if you've read to the end of the Learn Your Haskell book, you know that the last chapter is about zippers. And the idea is that a lot of problems in computer science can be expressed as having a data structure and a pointer to somewhere in that data structure. And you might want to move the pointer around or maybe mutate the values where the pointer is. And the problem is, how do you do something like this in a functional language that certainly doesn't have explicit pointers? And the answer, given in a paper by a guy called Gerard Hewitt, which I'm probably horrifically mispronouncing, is to use something called a zipper. So the way that a zipper works, it's like a data structure that has a focus point, right? So the focus is on one of the values, and then you have the list of things before that value and the list of things afterwards. So if we wanted to put the focus on 3, say, then this value would be 3, the list before would be 1 and 2, the list after would be 4, 5, and 6. And this lets you quickly move around and change the focus of where you're at inside this data structure. There's a minor niggle, which is that you have to keep the first list in reverse order, which I'll show you why in a second. So you can write code like this. So this let z equals stuff is this list up here, but represented as a zipper instead. So it has the focus on 3, and the first list, which we store in reverse order, is 1 and 2, and 4, 5, 6 is everything afterwards. And then you could write an operation called write, which means move right in this data structure, which moves the focus from 3 to whatever's to the right of it. In this case, 4. And this is a fast operation, because all you need to do is deconst a value from the front of this list, and put the 3 on the front of this list. Right? This is the reason for storing first list in reverse order, because otherwise you'd have to append something to the end of a list, which would be slow. It would be order length of the list rather than constant. And you could do that again and move the focus again to 5, and you could have an operation left, which moves the focus back to the left. It's a nice exercise to code up the zipper type and write the left and right operations for it. And this is something that's used all over the place. So it's used in xmonad to store which window is in focus. I've seen people write text editors in Haskell and use a double zipper. So one zipper on a particular line to keep the focus where the cursor is on the line, and another zipper to keep the focus on a particular line in the file. Zippers aren't completely fundamental, though. We can break them down, we can modularize them. Okay, so we're functional programmers, we like everything to be nice and modular. So a zipper really has 2 different concepts in it. It has the concept of where you are, where your focus is, and it has the concept of the data which is there. We can split them apart, and the piece of data is easy. It's just an int or some other type, and the focus, the where you are in the data structure, is the interesting part. And this, in the literature, goes by the name of one-hole context. And it's basically a way of tracking where you are in a list. So we could, this is clearly not valid code, but we could represent the one-hole context of this list by saying, well, a list of 1 to 6. And then if we want to get a zipper, we'd just pair that one-hole context up with a piece of data we want to go in the hole. And that's exactly the same thing as having a zipper. We just split it up into the data that goes in the hole and the thing that tells you where the hole is. So why am I talking about this? Well, we'll figure it out if I do a couple of examples and show you what the one-hole contexts for some pretty simple types are like. So x, just the singleton type, just a single type variable, x. If you want to ask what the one-hole context of this is, well, there's only one place to put the hole, which is to take out whatever's in the x and put a hole there. The hole is all it is basically a placeholder saying we don't care what's here, we're going to put a value in later. And that's just saying we have a unit there. So the one-hole context of this singleton type x is just a unit, right? When we paired it with an actual x, that would then go in the hole, and we'd have 1 paired with x, which we already know is just the same thing as having an x. If we had a pair instead, so a pair of x and x, which in our type world we write as x squared, and we say one whole context of this, well, we can either put the whole in the left-hand side of the pair, or we can put the whole in the right-hand side of the pair. So we have a sum type, which is two pairs, one of which has a hole on the left, one of which has a hole on the right. And this hole is just the same as unit, right? It's just a placeholder where we're going to put something later. So this is just x plus x, which is the same thing as 2x. So this is a neat interpretation of it, right? So saying x plus x is the same as 2x, you're saying if you've either got something with a hole on the left or something with a hole on the right, that's the same as saying we just have an x and then a boolean, this 2, which tells us whether we're on the left or the right, where the hole is. We could do the same thing for a triple, so something of type x or x cubed. The hole could now be in the first slot, the second slot, or the third slot. So we end up with a sum type like this. And each of these terms is an x squared. And you have 3 of them because that 3 tells you where the hole is. So you have 3x squared. So if we collect these together, I've said that the one whole context of x is 1, of x squared is 2x, x cubed is 3x squared. And if you've done any calculus at any point, you might start to recognize this. So if we start with the thing on the left and differentiate it, you get the thing on the right. This is kind of neat. And in fact, it continues to work. And this was noted in a paper by Conor McBride, which has this title: The derivative of a regular type is its type of one whole contexts. I'm going to skip over what he means by a regular. Just for the moment, imagine he means type. And I'll talk about regular types towards the end. So I thought this is absolutely mind-blowing. The fact that you can take something like differentiation, which is clearly a concept from calculus, which is to do with continuous stuff, invented by Newton in like 16 or 17 something, for dealing with rates of change and slopes of curves and areas under curves, and apply it to type theory, which is something which wasn't even a thing until the 1970s. Someone might correct me on that. Right? I thought this was amazing. So let's explore this whole calculus of types a bit and see how far the correspondence goes. So I'm going to use this weird curly D guy to mean take the derivative. Okay? It saves on some writing. It makes the formulas look prettier. I'm a mathematician. I don't like writing much. So you know that if you take the derivative of a constant, you just get 0. So what's the type interpretation of this? Well, taking the derivative is like putting a hole in something. So you have to have a place where some data was, and then you put a hole where the data was. But something which is just a unit doesn't have any data. Right? There's just one value there. You can't plug data in. So it doesn't make sense to differentiate it. So you couldn't have a one whole context of unit. There's no such thing. So we say that's just 0. That's void. Right? It has no values. We already know that if you have a singleton type, something on its own, and you put a hole in it, you just get the unit type, and the unit is a placeholder, which is the hole where you're going to put some data later on. So that's neat. That works. That's valid calculus. If you have 2 different types, an F and a G, and you say, I want to put a hole in this type, so it's either F or G, well, you have to choose. Do you put the hole on the left side, or do you put the hole on the right side? So saying, let's put a hole in an either F or G is the same thing as saying we've either got a hole on an F, or we've got a hole in a G. And this, again, is valid calculus. If you have 2 functions and you differentiate their sum, that's the same as differentiating them both and adding them together. Differentiating products is a little bit trickier. So if you remember any of your school calculus, you recognize this as the product rule. So it's saying if we have a pair, an F and a G, and we want to put a hole in that, well, what can we do? We can either put the hole in the first element of the pair, in which case we've still got the second one, we haven't touched that, so that's an F with a hole in it and a G that we haven't touched. Or we could put the hole in the right-hand side of the pair, the second element, in which case we haven't done anything with the first one. So here's our second element with a hole in it, DG, and here's F, which is the first element of the pair, hasn't been touched yet. So this product rule, referred to as the Leibniz rule, invented by Gottfried Leibniz in 17-something, has a type interpretation as well, which I think is awesome. This last one is a step more complicated again, so it's totally acceptable to have switched off at this point. This is saying that if you have an F of G's, so F and G are both lists, a list of lists, and you want to put a hole in that, what you have to do is say, well, we first put a hole in the outer structure, so in the F, and then that hole goes all the way through to the inner list as well. So we put a hole in the inner list, which is the G in this case. So we've got two levels here. We've got our outer level, which has a hole in it, and otherwise it's still got a bunch of G's inside. And then we've got the inner level. So we're saying we need to keep track of the location of two holes at once here. Right? So we need to keep track of the location of the hole in the outer level and in the inner level. And this is called the chain rule in calculus. You may have used it. So all of these rules which apply to calculus of functions, real numbers, continuous things, rates of change, all have type level interpretations as well in terms of putting holes in data types. A neat thing you can do is take the functions that we already had, so the expressions for types, and start differentiating them as if they're just normal functions. Okay, do some calculus on them. So we knew that a list is 1 divided by 1 minus x, which we said makes no sense, but let's differentiate it anyway and see what we get. And if you apply some rules of calculus, the quotient rule and the chain rule and this kind of thing, you eventually find that the derivative of this is 1 over 1 minus x squared. Well, that's just the square of the thing we started with. So that's just a list squared. So we're saying that on the type level, the one whole context of a list is list squared, or a pair of lists, which is what we saw way back a few slides. Right? So you have the list of stuff before where you put the hole, and the list of stuff after where you put the hole, and then in between those two lists is where your focus is, where your hole is. We can do it for trees as well. So our equation for trees was t is 1 plus x times t squared. We could do it with this nutty square root thing that we saw, but it's actually just much easier to work with this, and you end up having to do a bit of implicit differentiation. So when we differentiate this, this guy just goes away completely. Differentiating 1 gives you nothing. And then applying product rule and the chain rule to this guy, you end up with this quite complicated looking type, which has a dt on the left and the right side. But that's fine, we can just solve and find out what dt is. Okay, so let's go a bit mental with types again. We collect all the t's on the left-hand side, we divide through, and we find that the one whole context of a tree is 2 trees divided by 1 minus 2 times an x times another tree. But we know what dividing by 1 minus something is. That's just a list. So this is the same thing as saying a tree with a hole in it is 2 trees, and then a list of a triple of booleans, x's, and other trees. This project makes almost no sense at the moment, so I figured a picture would help. So here's a binary tree, and it's got a hole in it. Bless you. Here's the hole in this binary tree. And we can look at this equation up the top and give it an interpretation in terms of this picture. And it becomes a bit clearer if we start drawing circles around things. So we know that a tree with a hole in it is 2 trees. Those trees are left and right branches just beneath the hole. So there's a tree with 1 value here and a tree with 3 values here. And then you have a list of things which are triples, a boolean, a value, and another tree. And this is this list going up to here. So the first value in the list is the value immediately above you. So it has a value, which is this orange dot, and it has another tree, which is this guy, and it has a boolean, And the Boolean is telling you which side this is on. Okay, so here the tree that you haven't really touched is on the left. Here there's a tree on the left, and here there's another tree on the right. So this is the type interpretation of this equation at the top, done as a picture. Okay, I promised to briefly mention non-regular types. So regular types are what we have dealt with so far. And the thing is, when you write a Haskell data type, there's an ordering of the arguments to all of the constructors. But you might conceivably have a type where you don't really care about the ordering of things. So, for example, a bag is a data type which holds a bunch of values, but you don't care about what order they're in, unlike a list, where you do care. You know, the ordering is the whole point of having a list, right? If you didn't care about the ordering, you'd use a different data type. So a bag has a bunch of stuff with no order. A uniqueness list is a list. It has order, but it has the restriction that all of the elements in it are unique, so there are no duplicate values in it. So if you try and const something onto the front of it and it's already in the list, you just get the same list back again. And a set is something that has both of these properties, right? So it has unique elements and you don't care about the order of the elements in there. So the set 3, 2, 1 and 1, 2, 3 are equal, whereas the list 3, 2, 1 and the list 1, 2, 3 are not equal. And there are various other more exotic data structures, so cyclic lists, where you care about the order, but only up to cyclic permutation, so the tail of the list joins onto the end. And these are all non-regular types. And you can ask if they have an interpretation in our algebra as well. So I'll take the example of sets, because they're the easiest one to work with and sort of fit into the algebra. You can do it with all the other types as well. It's just more complicated. And to understand sets, I'm going to first talk about fixed size sets. Okay, so sets with a particular size. So set n is the type of sets of size n. Okay, so all sets that have two elements. So set naught with values of type x, well, it's just an empty set, right? It's a set with no elements, and there's only one of those. It's just the empty set. So let's call that 1. Set 1 is all sets that only have one value. And if you have a set and it's only got one value in it, you might as well just have the value on its own. There's no point having the set. So that's equivalent to x. And then set 2, this is where it starts to get complicated. So we're looking for the data type of all sets with two elements, with the restriction that the order doesn't matter and that the elements in there are unique. And we can do this with a counting argument. So for the first element, we can put anything in the first element. Right? We can say if x is bool, we can put either true or false in there. And then when we choose something for the second element, we have to put something different in. And we've already used one element, so there's one fewer thing we can put in as the second thing to go in our set. And so we write this as x minus 1, and this is the subtraction types that I referred to do with uniqueness of types. But then we know that the ordering doesn't matter, so we want 1 and 2 to be the same as 2 and 1. And the way we deal with it is saying, well, we're overcounting. Right? So if we just say, well, think of all the things we can put in the first slot in the set, and then all the things that can go in the second slot, as long as they're not the same as the first one, we end up double counting, because we try and put 1 in the first slot and 2 in the second, and later on we try and put 2 in the first slot and 1 in the second slot. So everything is counted twice. So we divide by 2. Okay, this is somewhat specious. We divide by 2 to say we've overcounted, let's just divide everything by 2, and then at least this, interpreted as the number of different sets of size 2, will be correct. Whether it makes any sense on the type level, who knows. And we could carry on doing this, and for sets of size n, you find that you get this expression up here. So this is saying in the first slot you can put anything, then you've used a value, so you can't put that in the next slot, and then there'll be an x minus 2, and you go all the way down to the nth slot, where there are n minus 1 values that you've already used, so you're much more restricted into what you can keep putting into your set. And the neat thing here is that say x was 2, right? And we say how many, so x is, how many sets of booleans are there of size 3? Well, we know there aren't any, because once you put true and false into your set, you've got nothing left to put in there. And this would have an x minus 2 term somewhere in the middle, which is equal to 0, so the entire thing would be 0. this dividing by n factorial at the end, this notation with the exclamation mark is math notation for n factorial, is because if you've got a set of n elements, there are n factorial ways to permute them, and so you don't care about order, so you just divide by the number of ways to permute all the elements in your set. And we write this using this notation to be concise. This is called, this x to the power n with a little underline, is called a falling factorial. It's just shorthand for this thing at the top. And then the type of sets of any size, you just get by summing up the empty set and the set of 1 element and 2 elements and 3 elements. So this is the type expression for sets of any size, which is nice, but it doesn't make I can't look at this and say this makes sense as an equation which represents sets. So I'd like to try and make sense of it, and I'll do that by introducing an operator which I use this triangle, so Greek letter delta, which is called a forward difference operator. So what we're saying is that the forward difference of f evaluated at x is f at x plus 1 minus f evaluated at x. Makes sense if f is a function and x are numbers. Might not make any sense for types. In fact, it does have a neat type interpretation, which is doing this to a type, this forward difference, is equivalent to putting all possible holes into the type. So instead of just putting one hole in when you differentiate, you're putting all possible holes in. And you can do a little bit of calculus and see this for yourself. But the cool thing is, if you take this operator and apply it to this, and do all the algebra and work it out, you find that you get the same thing back again. So this is a fixed point of, set is a fixed point of this forward difference operator. So what's this telling us? Well, it's telling us the forward difference of a set is just a set, and the forward difference of a set is a set of x plus 1s minus a set of x's, and that's equal to a set of x's. We don't really understand this subtracting of types, so we'll put it on the other side. So a set of things of type x plus 1 is the same as having 2 sets of type x. But we already knew that there's only one set of voids. So if x is void, right? The only way you can have a set of voids is if it's empty, because you can't get any void values to put in there. So this is basically a recursion, right? This is a recursive definition of the set type, where now x's are types instead of values, and we could just keep resubstituting in, and eventually find that the type of set is 2 to the power x. And 2 to the power x, we know, is a function type, right? So this is 2 to the power x is the set of functions from x to bool. And the nice interpretation here is that for each x, it's either in the set or it's out of the set. So if x maps to true, it's in the set. If x maps to false, it's out of the set. That's the end. Code for this talk and the presentation will go on my GitHub account after the talk. Thank you very much. Yeah, so if you wanted to do a little bit further reading, I recommend the blogs of these guys. The start at the bottom, so the type calculus stuff. So Conor McBride is the guy who wrote the original paper. The derivative of a regular type is its type of one-hole contexts. So search Conor McBride's website. He's got a link to all of his papers there. Dan Poponi, who you may know by his name SIGFPE, has a blog, sigfpe.blogspot.com. If you just search SIGFPE, you'll find it, where he writes about a whole load of stuff, including types, the calculus of types, innovative interpretations of monads, physics, visual effects, like the whole thing. It's a really interesting blog. I recommend reading it. At the top, if you want to make more of the connection with the counting aspect, so working out how many different values a particular type has, Andrei Joyar is a mathematician who was working in the 1980s, I think, who wrote the original papers on this. But actually, Brent Yorgi is more computer science focused. He does a lot of Haskell. He has a really good blog called Brent : log to string or something. It's a Haskell pun. If you search for Brent Jorgen and find his blog, he writes a lot about combinatorial species, which are a way of looking at types which are a little bit closer to maths and get rid of a lot of the messiness, so don't have undefines and always have unique values and that kind of thing. So you can do nicer maths with it, but it doesn't map onto Haskell quite so well.
Of course, we're very happy to answer any questions.
Absolutely. Yeah. Yes. Yep. I'm not going to say I know the answer to that. So there's an interesting point to be made. So I've written set x equals here. If you look at the expression for sets we had up here, clearly everything in this expression is of finite size. There's no x to the power infinity. But on the other hand, there is a function const true, which is a set with infinite size. So this doesn't quite work, and I suspect this may be related to the question you're asking, but I don't understand it. If anyone does understand it, tell Brent Jorgen about it. He'll be delighted.
Any further questions?
So that particular paper that I mentioned, the one by Tom Leinster, he's not really talking about types. Like, he's not a computer scientist, he's a mathematician, just with a slight computational side. So he's talking about semi-rings, which are an algebraic structure, and types just happen to be an instance of semi-rings. So he's doing a slightly more general thing. So it holds in full generality for anything that's a semi-ring. I don't know. The question was, so is this correspondence between complex or imaginary numbers and types? I'm not quite sure what the question was. Yeah. The question is about the rules. So when can you take something which is valid for complex numbers and turn it into something valid for types? It doesn't always work, and so you can show that the type of binary trees, for example, if you take some value that satisfies that equation and start playing with it, you can end up with t to the power 6 equals 1, right, which would be true for complex numbers that satisfy that equation, but not true for types, right? So 6 binary trees are not the same as unit. But it is true that 7 binary trees are the same as 1 binary tree, so t to the power 7 is equal to t. So there's an isomorphism. If you have a 7 tuple of binary trees, you can map that into a single binary tree, and you can do the reverse. So, yeah, there are certain, there are, yeah. Sorry? Relative type? Did I say regular type? Yeah, sorry. So everything we dealt with up until this bit about non-regular types was a regular type, and then non-regular types are this more special thing.